Section 7.7 deals with what are known as improper integrals. An improper integral is the type of integral that arises frequently in the engineering field of signal processing and also in probability and statistics. And it can really be described in the following manner. Throughout the semester to date, when we compute a definite integral, the endpoints have always been finite numbers, like 1 and 5, 2 and 4, something like that. And the function has always been continuous between the endpoints. There aren't any vertical or horizontal asymptotes. Well, we say an integral is improper if it violates one of those conditions. More precisely, an integral is improper if at least one of the endpoints a or b is infinite, or if f has a point of discontinuity somewhere between a and b. So, for example, here is the function 1 over x to the third, the improper integral of 1 over x to the third dx from 1 to infinity. It's an improper integral because one of the endpoints is infinite. And what we're attempting to describe is the area bounded by the graph, the horizontal axis, x equals 1 and x equals infinity. Now I've drawn that area right here, and I started the graph at x equals 1, so it actually goes through the point 1, 1, which is up here. And what we're attempting to determine is whether this area all the way out is a finite number. How much paint does it take to cover up that shaded region? And that's what that's what this improper integral is attempting to describe. Another example, similar. The integral from 0 to 1, 1 over the square root of x dx. Now 1 over the square root of x is undefined or discontinuous at the origin. So what this integral is trying to do, it's trying to describe the area between x equals 0, x equals 1, and the graph of 1 over the square root of x. And I've actually shaded that here. And we can see that the graph keeps going up and up. So we might wonder if that area works out to be a finite number. So again, this integral is improper because there's a point of discontinuity, namely 0, that is one of our endpoints. Other examples of improper integrals. 1 over x, the integral of that from 1 to infinity. It's improper because one of the endpoints is infinite. The same thing is true about this, the integral from minus infinity to infinity, 1 over x squared plus 1. Or the integral from 0 out to infinity of x e to the negative x. 1 over x from x equals 0 to x equals 1 is also improper because 1 over x is undefined at the origin. The integral of 1 over the square root of x minus 2 from 0 to 2 is an improper integral because this function is undefined at 2. Okay. So how do we evaluate or attempt to evaluate improper integrals? That's the issue. Let's take a look at the integral from 1 to infinity of 1 over x to the third dx. Now, we would know how to integrate this if this was from 1 to 5, 1 to 10, 1 to 20. So what we'll do is we'll take a step back and we'll make it a proper integral. We'll integrate from 1 up to b, where b is just some other variable or parameter. And we're going to find a formula for this definite integral that depends upon b. And then we're going to ask ourselves, what happens as b gets larger and larger? What happens as b becomes infinite? So let's integrate 1 over x to the third dx from 1 to b. That's a b, not a 6. If I compute the antiderivative of this using the power rule, I get minus 1/2 x to the minus 2. And I'm going to substitute 1 and b in. If I substitute b in, I get minus 1/2 b to the minus 2. And if I subtract what I get when I plug in 1, I get minus 1/2. So that works out to be just 1/2 minus 1 over 2b squared. Now let's make a table of values. Over here, I'll use the value of b, in other words, my upper endpoint. And then in the right-hand column, I'll use the values of the integrals. So the integral from 1 to b, when b is 5. If I substitute 5 into this formula and simplify, I get 0.48. If b is 10, then I'm computing the integral from 1 up to 10. And if I plug 10 into this formula, I get about 0.495. If b is 100, And if I use 100 as the upper endpoint, this works out to be about 0.49995. And we can see that these values are getting closer and closer to 0.5. So we would write that by saying the limit as b goes to infinity of this, which I've written right here, is equal to 1/2. So from the table, we can see that this becomes closer and closer to 1/2 as b gets larger and larger. In the terminology, we say that the integral from 1 to infinity of 1 over x to the third dx is an improper integral that converges to, or in other words, equals 1/2. So going back to the picture we had a moment ago, if you asked me how much paint I needed to cover the shaded region, it would only be 1/2 unit. Now we can see this algebraically from the formula as well. If I write down the formula for the integral from 1 to b of 1 over x to the third dx, which I computed above, I'm taking the limit as b goes to infinity of 1/2 minus 1 over 2b squared. That's what we got right up here. And if I let b get larger and larger and larger, 1 over 2b squared becomes smaller and smaller and smaller, and we're left with 1/2. So that's showing algebraically that the improper integral converges to 1/2, not just using the table. Let's take a look at the other example. 1 over the square root of x. Okay, so it's improper because the lower endpoint is 0 where the function is discontinuous. So we're going to make it a proper integral by changing this 0 to some letter a. We will evaluate this integral, and then we'll have a formula in terms of a, and we'll see what happens as a gets closer and closer to 0. If I take 1 over the square root of x, and if I integrate it using the power rule, I get 2x to the 1/2. I substitute my upper endpoint of 1 in, my lower endpoint of a, and I get 2 times the square root of 1 minus 2 square root of a, or just 2 minus 2 root a. Now, we take the limit as a goes to 0 of this quantity, which is the limit as a goes to 0 of 2 minus 2 root a, and as a gets smaller and smaller, the square root of a will become closer and closer to 0. So the whole quantity will become closer and closer to 2. So in this case, we say that the improper integral from 0 to 1, 1 over the square root of x dx, converges to 2, or in fact equals 2. So in terms of my picture, it only takes 2 units of paint to cover the shaded region. Let's do another example. Okay, we're going to look at the improper integral from 1 out to infinity, 1 over x dx. First thing, we make it a proper integral. We look at the limit as b goes to infinity, the integral from 1 to b of 1 over x dx. Now let's write down the integral from 1 to b of 1 over x dx. That's the natural log of x evaluated at x equals 1 and x equals b, which is the natural log of b minus the natural log of 1, which is just 0. So looking at this limit, we have the limit as b goes to infinity of the natural log of b. Now the graph of the natural log looks like this. So we'll have b and then the natural log of b, and it looks something like that. Sometimes it's misleading that this graph has a horizontal asymptote, but it doesn't have any asymptote. As b gets larger and larger, the natural log curve grows without bound. It does so quite slowly, but it in fact grows without bound. So in this case, the limit does not exist. So we say that the improper integral from 1 to infinity of 1 over x, it diverges. Okay, your assignment for class is to evaluate the improper integral from 1 to infinity of 1 over x squared dx. Determine whether it converges, and if it does converge, what it converges to. And do the same thing for the integral from 0 to 1 of 1 over the cube root of x. Now this integral is improper because of the upper endpoint of infinity. This integral is improper because the lower endpoint, which is 0, where the cube root of x, this is the cube root of x, is discontinuous. So do those two for class, please. See you then.